Hello everyone and welcome to today's seminar on what is a restricted computation domain really? Today we'll discuss the broad idea of a restricted computation domain and how we can access them or apply them from Python. We'll take an in-depth look at the computational efficiencies offered by NumPy and how to use it effectively, so we'll cover some of the rules there. And we'll even talk about some other restricted computational domains as well. Things like what can pandas do that NumPy can't, and what can polars do without relying on the NumPy backend. But we have so much to cover here together. But first, the first point that I want to address. Is Python really that slow? We're talking about restricted computation domains, we're talking about efficient computations, but is Python really that bad? And if so, why? Well, one of the biggest reasons for Python being computationally slow is due to its dynamic nature, right? We don't have statically typed variables that we can rely on to introduce a lot of optimizations to our computations. Instead, we're willing to bet that some of the computational inefficiencies are going to be kind of scooted to the side in favor of developer efficiencies. With dynamic typing, allegedly, right, we can prototype a little bit quicker, we can work with our code and make changes to it quicker without having to worry about so many of the side effects. But what does this mean in terms of Python? Well, in terms of Python, it means I can write a very valid function like this. This function takes two arguments, x and y, and it returns their addition. Now, what does that mean to add x and y? You can probably intuitively think I can create this function, f of 1 and 2, and you'll think, okay, well 1 plus 2, that's going to be 3, so let's take a look at the result. And it is in fact 3. I can take this a step further and I can turn these into strings though. And now, instead of getting 3 as my output, I get 12. Well, 12 the string, right? Not 12 the integer. I can go even further though. Instead of using string, I can use lists. I can use absolutely anything that defines, right, our add, addition, double underscore, or magic method. And so what this tells me for Python is that although its dynamic nature may make it slow, it does make it incredibly flexible. This means that Python does not know in advance what two things it's going to be adding together. Instead, at runtime, when we go to execute this line or this line or this line, this function has to do a check. Can these two things be added together? And if so, what do we need to dispatch? What binary operation do we need to dispatch in order to add them? And so if I do something like this, take a string and an integer, right, we get our error here. We get a type error. And this type error is telling us at runtime, hey, I tried to add a string to an integer and I just don't know what to do. This means that Python is taking time in order to verify that these two things can be added and then actually dispatch the correct implementation of how to add them. And this does add a little bit of overhead. And while we're speaking of overhead, when we're talking about Python being slow, the most common example are function calls. You may have heard this on social media or blog posts that you have read, but Python function calls are slow. They just take forever because one Python function call is going to be multiple calls right in the lower level implementation. And so we can actually time this. So all I have here is just a quick little context manager timer. And what I'm going to be doing, I'm going to be timing two things, and I'm going to be running them 100,000 times just so we can kind of boost our signal just a little bit. But here you can see I've assigned two variables, A and B. Inside the body of this for loop, all I'm doing is adding them together. And so when we do that and we compare this against our other implementation, which instead of just adding two variables together, we're going to create a function that simply does the same thing. And so the only overhead that we've added here is the overhead of actually calling a function. And you can see that when we run this, it adds a little bit of time. And you can think, well, if I call a function just once, that's not that much time. But if I call it 100,000 times, we start to see, right, this buildup of how long it takes to add two things together or perform a function call, right, that adds two things together. And so when we talk about computations, we're typically thinking in terms of large quantities of data and very repetitive operations. And these are two things that Python does not provide any kind of a priori optimizations for. And I will say this, Python does offer a couple of optimizations, right? When parsing byte code, we actually see this optimization right here. And you can see this is actually due to Python simply just evaluating this and loading it as a constant before it actually executes the code. This is a bytecode level optimization. But if I were to take two, say, lists or arrays, right, of large numbers and add them together, if I were to repeatedly have to call a Python function all of those, we can start to intuitively think that evaluating that function over and over and over and over again at the Python level is going to be expensive. And so this is why we rely on other tools in order to perform and carry out heavy computations for us. Specifically, we'll be talking a fair bit about NumPy here. And so let's go ahead and compare kind of the most basic NumPy structure, right, the ND array or the array, and our built-in Python list. They are similarly looking, right? If I were to create a Python list, let's go ahead. Here we have a NumPy ND array, and we have a Python list. So I'll call this my PyList, and put 4 numbers in there, and we'll put, right, just those same numbers into a NumPy array. When I print these out, NumPy R, this should be PyList. When I print these out, you can see, okay, well, the representation of my NumPy array doesn't have commas where the Python list does have commas. That's not the most interesting difference between them, but we can see that the representations are similar. But the thing that we think about when we think about the Python list is the Python list can be used to store very different values. So let's go ahead and put a string in here. You can see that in my Python list, I actually have 4 integers, 1 through 4, and then I have a string, and it's a very valid string. On the other hand, my NumPy array, well, NumPy is making an assumption about the data. It's applying one of its rules in order to work with the data efficiently. And so what NumPy is actually doing is it's identifying that, okay, these first 4 things were integers, but this 5th thing, well, this was a string. And so in order to store something in a NumPy array, they all have to be of the same type. This is what we call homogeneity. And so we can start to realize that these two data structures serve entirely different purposes. The Python list is not constrained to containing a single type. The Python list is simply used to store collections of objects. Now, I will say that it is loosely heterogeneous. And the reason I say that is because the Python list can store different data types, but is it the most useful thing? Would I ever actually create a list like this in my program? Probably not, because the most common thing that you're going to do with a Python list is iterate over it. Then, when I'm iterating it, I'm probably going to perform some uniform action to all of my elements. And so we start to realize, okay, although it can contain differently typed objects, we don't usually use the list for this purpose. We usually use it for data structures of similar types, not necessarily the exact same, but definitely not extravagantly different. And so this is the stark difference between the Python list and the NumPy and D array, is Python list can contain different types, and the NumPy and D array can only contain elements all of the same type. This allows NumPy to work very efficiently when performing computations because it already knows the type of every single object in it. And so it doesn't need to perform any checking, oh, is this an integer and is this an integer? Okay, if so, I can add them together using integer addition. NumPy already knows this in advance, and so we can take a lot of shortcuts that Python can't. And so let's talk a little bit more about some of these differences here. We see in this example, I have a Python list with the integers 10 through 13, 13 included. And in our NumPy array, we are creating the exact same representation. What I want to highlight here for you is that our NumPy array has a good amount of metadata attached to it. Specifically, we know the data type. We know that these are all 64-bit integers. We also know the shape of this thing. So the Python list also knows its shape, or knows its length, I should say. They don't really have a shape in multidimensional regards, but it knows the shape of each of its dimensions. If I were to change the dimensionality of this array, we can see that the shape has changed, but the data type has remained constant. And so when we work with Python list versus NumPy and D arrays, we can start to reason about, okay, the NumPy and D array knows a lot about its contents. In fact, it knows the location of every one of its contents in memory. What happens when I need to look up a specific value in a Python list? When I perform this action, say, get me the second element of my list X, it actually needs to go into the list, locate the second element, and then it has to unbox that value. It doesn't know right away that this is the integer 11. This is simply at the implementation level, this is a CPython object. And so it has to ask, okay, what are you? Okay, now if you want to do something with it, then it has to go and dispatch the correct method. Whereas the NumPy and D array, it already knows what all of its contents are, and if I were to perform something like an action like this, use this first example here, if I were to look up the second element like this, what NumPy does, or what Python does, is it looks up the starting point, the memory address of the starting point of this array, and then it uses the metadata from the array to skip right to the exact position where this integer starts, and it knows exactly the correct bit length, right, how many bytes to read, in order to actually extract this value. And it can actually intuit this, or knows this information from the data type, from the shape, and from our strides. And so the striding is all about how many bytes do I need to skip to go from one value in my NumPy and D array to the next. Whereas with Python, our list is simply a collection of pointers, and we have to look up that pointer, and then we have to go chase it down. Whereas NumPy can take a little bit of shortcuts, especially when trying to iterate, say, over these things in sequence. It's very effective at the NumPy level to iterate over these things in sequence, not at the Python level, right? Not a Python for loop. And so we can actually manipulate these strides a little bit to find out more what they mean and what they do. If I were to change the dimensionality of this array, go ahead and just print this out for you. We now have a two-dimensional array, right? This is 2 rows by 4 columns, so to speak. The data type remains constant, the shape has changed, but now we have another layer on our strides. And let's go ahead and just compare this. Our strides before was simply 8. Once I change the dimensionality of this, we have 32, 8. And what I said before, when it was simply just a single value, I said this is the number of bytes that NumPy has to skip to go from one value to the next in the lowest level dimension. So in order to go from our value of 10 to our value of 11 in memory space, right, we need to skip 8 bytes. This first number here, however, is how to get from one row of my NumPy and D array to the next. And so we can actually broadcast, or we can align this up. Now I have 3 matrices, all of 2 dimensions, so a 3-dimensional ND array here. And you can see that my striding has changed. In order to move from one column to the next, right, the lowest level, I just need to skip 8 bytes. In order to go from one row to the next within, right, one of these 3D structures, I need to skip 32. And in order to go from one matrix to the next, or one 2D shape to the next, so to go from this 10 here to this 10 here, well, I just need to skip 64 bytes. All of these data in memory are simply contiguous. They all exist one after the next, after the next, after the next. This allows NumPy to very efficiently work with these values, access them, and skip around to specific places. Additionally, Python lists are dynamically sized, whereas NumPy and D arrays are statically sized. In order to ensure that all of our values maintain that spacing, right, that uniform one value, then the next value, then the next value by some amount of bytes? Well, NumPy has to allocate a specific amount of memory and then start filling in those values. Whereas Python, well, the pointers in the list, right, those are contiguously stored, but those don't take up a lot of space. And the Python list is also a little bit smarter of a data structure. It is built for dynamic resizing. So if you need to add a bunch of things to a list, it'll actually over allocate how much memory it's going to need so that it has some empty space to fill in. Whereas NumPy does not do that because it's just a little bit more efficient. It doesn't try to be a smart, right, data structure because you want to be very memory efficient with your NumPy and D arrays. And so we can do just a quick little test here. We can take our Python list and we can see how long it takes to append 1,000 values to that list. We can take a NumPy and D array and we can perform the same operation. And we can see, wow, it is magnitude slower. What's going on here is that in order for a NumPy and D array to access or to add a new value into it, if my NumPy and D array is only this large and I need to add a third value, right, that's outside of how much memory I've already allocated, NumPy has to go, okay, I need to allocate new space of memory that's just one size bigger than what I previously had. I need to go find somewhere else to get that. Okay, now I have all of my values. I need to copy over the previous two values, and then I add my third in. So we're performing a bunch of copying here and new memory allocation, whereas Python doesn't need to do this step because it's already over allocated how much space it needs in the list. And so it can very easily just add in those pointers as needed. Finally, we're talking about restricted computation domains here, and there are rules. In order to work efficiently with tools like NumPy, you simply need to follow their rules. So if we know that creating copies is a little bit expensive, what we can do is instead pre-allocate, right, an array, and then we can simply update those values. We don't get the same exact performance as we do from a Python list, which is very optimized for growing, but we can see here that assigning values into a pre-allocated NumPy and D array is a valid solution if we were concerned with this kind of performance benefit. So that's just one of the rules that we need to abide by. What are some of these other rules? Well, we have broadcasting, which is the alignment of one or more NumPy and D arrays to each other. We have views and copies, which we need to understand in order to really make sense of how and when NumPy will tap into that, oh, it's making a copy that's a little bit expensive, maybe I want to avoid this operation. And then we also have vectorized operations, which vectorize is kind of a loose word here, but we'll get into the nuts and bolts. Essentially, we're just using it as a way to abstract out a for loop. That's the terminology that we're using here, and that's the terminology NumPy uses in. There's a couple other definitions, but I don't want to get too into them. So let's see if an array will broadcast, and what does that even mean? Well, if I have these three arrays, they'll have very similar size to each other, except for C, which is one element shorter. Our first array, I can actually take that array and I can do a +1 operation. You'll note that this is very different from a Python list. If I did a Python list plus the integer 1, I would get that type error and it says, I don't know how to add 1 to a list. Whereas the NumPy and D array, it says, oh, you want me to add the integer 1 to every single element in this array. And the reason it can do this is because it broadcasts these two things to each other. It's actually taking this Python integer 1, it's turning it into a NumPy and D array, and then it is stretching that so that it lines up with this original array here. So you can think of this as doing something akin to this. 1, 1, 1, 1. And so we end up adding, right, each of those values to one another. But there is a more complex set of rules that we need to follow here. Instead of just adding a single value to an array, we can actually add two arrays to each other. Well, they already line up, and you can see that vertically, right? They line up very nicely here. If they have a different shape or a different size, well, that's when we start hitting problems. The way that we can circumvent this is we need to ask ourselves, what are we really trying to do here when I say A plus C? Do I want to add 10 to 30, 11 to 31, 32 to 12, and then drop the 13? Maybe I actually want kind of the outer product or the outer sum of these things. I want to add 30 to every value in here. I want to add 31 to every value in here and repeat the process for 32. All this takes in order to do that is just a little bit of reshaping. And so what I do here is I'll actually change the shape of my array in NumPy, which is a very cheap operation. All we're doing is just changing some metadata attached to the array here, right? All the values are still stored contiguously. Then I'm using that to actually align against my A. And what we end up doing here, what we're looking for, is that for both of these shapes, this is the shape of C on top, and this is the shape of A. This one is kind of implicit, but when we perform alignment, we want to line up the shapes of these things, and we want to say, are the dimensionality exactly the same? Is this top number of 4 and is this bottom number of 4? Or if they're different, is one of the dimensions just 1? Those are the only two rules to broadcasting. You look at these from right to left and you start your comparison. So I know these two things will align because this value is 1 and this value is 4, and that meets my criteria. This value is 3 and this value is 1, and that meets another criteria, or the same criteria, indicating to me that these two things will align. We can also talk about using existing memory or allocating new memory in terms of views and copies. And so in Python, we know that if I need to make a new reference to the same object, I can simply just perform another assignment. And you can see on the bottom here that B is in fact A. And that's great. But what if B wasn't A? In terms of Python, right? Different objects, but would these point to the same array? All I'm doing is I'm saying B is the equal to the slice of everything in A. Did I just make a copy of A? Well, the easiest way to check that is to update something in B and see if it's reflected in A. And that will tell us, did I make a copy of it? Or is B also pointing to the same NumPy and D array as A is, despite being different Python objects? In fact, it is. And so this is the idea of a view versus a copy. If I create a copy of A, we see that my mutation to B does not affect A. If I do not make a copy, we see that if I update B in place, I also update A in place. And so this gives us a very interesting way of thinking about NumPy because we have our Python objects at the top level, but they are not necessarily reflective of the truth of which NumPy is holding on to as are these arrays pointing to the same point in memory, the same contiguous set of values in memory. And we can actually ask that to NumPy in a myriad of different ways. Specifically, we'll be using the shares memory function from NumPy. And you can see here from this, all I'm doing is simply just asking, does this specific subset of X share memory with X? Interestingly, you can see here that if I just subset 0, the 0th element, it doesn't share memory. That's because we're just getting a NumPy integer back in this case because it's A range 5. And this doesn't share memory with really anything. But if we get a slice of the array, well, this does share memory. This means we are not creating a copy. And this is actually very useful because by avoiding a copy, I'm avoiding a little bit of that overhead, and I can continue working with this structure in a way that might be more efficient. The only thing I need to be very careful of is I update this view in place, I will also update the original array, in that case X. But you can see here that all of our slicing and our reshaping operations, all they do is make views, and so they're extremely cheap because all we're doing is just changing some metadata associated with the array. We also have some fancy indexing, or as it's now called, advanced indexing. NumPy changed up the documentation probably a couple years ago or 2 years ago. But this used to be called fancy indexing, and what you can see here is that by passing in a rule or a Boolean mask or discontiguous integer positions, NumPy will return, right, an appropriately subsetted array, but it has to make a copy in order to do so. The general rule of thumb is if you can express your operation with a slice or by changing the strides that we looked at, and you can change those strides, then you'll get a view back. If you are using some advanced indexing techniques or doing anything that you cannot represent just in terms of changing the strides, then you will be a little bit out of luck. You'll be reaching for copies instead of just views. And so it's an important topic to be, or concept to be aware of, because sometimes you want to work with one versus the other. Now, the price of crossing the boundary. This is the most interesting part here, because we know that if I perform computations in NumPy, well, they'll work fairly quickly and they'll work fairly efficiently. If I perform computations in Python, well, we'll just assume that it's slow. But what happens if I start to intermix these two things? Well, let's go ahead. We have our Python x's here defined, and we have a similar NumPy and D array. And what we're going to do is we're going to use the Python sum on the Python list and on the NumPy array, and we're going to use the NumPy sum on the Python list and the NumPy array. We're going to see what our timing, which comes out to be faster. So going to import our product here because I want to pit these two things against each other. And I'll need my x name, x's in product of, should be funcs.items. So go ahead and grab these, and we'll grab our timer, which we already have imported. And we have our f name there, and we get our values here. And we'll just simply call f of x. What we can start to see here is that this was obviously the fastest, right? This was 3 times faster than second place timing here. And what this is, it's our NumPy sum against our NumPy x's. So kind of going with that rule of thumb, if you stay within NumPy, you're going to go fast and you're going to work efficiently. Additionally, in second place, this is kind of interesting now. If I don't even touch NumPy, all I do is use Python, I'm still going fairly quickly. And this was, what, 100,000 values? To sum up 100,000 values in this amount of time, just at the Python level, that's pretty good in my opinion. Where we start to see larger slowdowns is when we start to use, right, our Python sum on our NumPy array or our NumPy sum on our Python array. And so we have this idea of crossing this domain boundary will start to greatly slow down our programs and slow down our computations. And so I want to wrap you all with this. Restricted computation domains are a way that we can reach from a high-level programming language like Python to carry out some very heavy computational work. In order to work with restricted computation domains, we need to understand their rules, of which there will be a diverse set of rules. NumPy has its own rules, right? Broadcasting, understanding views and copies. Pandas has its own set of rules, right? Index alignment, which is similar to broadcasting. When Pandas actually has a fast path, and this requires some very specific knowledge, right? Pandas say string operations. If you do something like pandas data frame column a dot str dot capitalize, that's actually pretty much the same thing as just performing that computation or that capitalization on a string in a regular old Python for loop. And so you're actually not gaining any speed benefits there. Now with the PyArrow backend, this is starting to change, but it has not fully changed. And so if you really want to perform a lot of operations, say with a string data typed column in Pandas, it's actually more efficient to just call a single dot apply, grab each value, perform your, say, 3 different string operations, and then move on. Instead of calling .string.capitalize, .string.strip, .string.slice, you simply just do it in 1 apply instead of 3, which Pandas will a little bit mislead you into. The thing to be cautious there is Pandas could very well speed up the .string methods by pushing more of that computation down into PyArrow, which has a little bit better implementation of performing string operations than does the NumPy backend. Or I should say pure Python, because that's what Pandas is using. And so in order to work effectively with these tools, you need to understand their rules and how to stay within them, because if you try to follow some of the rules of NumPy, but keep dishing it back up to Python, you're going to encounter very large slowdowns to your computations. Similarly, in Pandas, right, if you perform a group by operation and then you use a .apply and pass in a Python function, now you need to pay the cost of evaluating that function per group that you have in your data set. If you have a large data set, this could be extremely slow. You want to stay within that restricted computation domain. But this does take us to the end of the time that we had allotted today. I wanted to thank you all for coming, and I hope to see you here again tomorrow for our micro training on how do I tighten my iteration loop, where James will share some great tips and guidance on how to program effectively and how to test and edit and repeat that process for your programs in a very efficient manner. Thank you all again for coming, and I hope to see you again tomorrow.